Yeah, yeah.
Okay, good. So let's start our today's seminar. And so we are happy to have Umut Varolgunes from Bogazici University. And he will speak about mirror symmetry via relative Floer theoretic invariants. So please.
Thank you. Thank you for the invitation. So this talk is not going to be very heavy on theorems. I hope, it will be some speculation. It will be a lot of conjectural things. So I apologize for that, but
No, you should be proud of that,
Okay, well, that's better for me. Okay, but yes, so most of it is conjectural. Okay, so I want to just start by kind of very briefly saying kind of what are the boundaries of this project. It's going to be vague, but I will make this less vague soon. So what I want to do is I want to do mirror symmetry, but I'm a symplectic geometer. I want to do it from a symplectic perspective. My goal is to understand symplectic manifolds. So I'm going to start with a symplectic manifold N, and this is going to be graded. So graded means its first Chern class is 0. But moreover, I also choose some trivialization of the top exterior power of the cotangent bundle or tangent bundle up to homotopy. Okay, so that's a grading of my symplectic manifold. All of my talk, I'm assuming this this very weak symplectic Calabi-Yau assumption, and I'm fixing this grading. Okay, so it's in the Calabi-Yau case, you can think of it as the choice of holomorphic volume form, but it's a much weaker, much softer data than that. Okay, so that's the first level of data. The second level of data, I want this symplectic manifold to be equipped with a decomposition. And the decomposition that I have in mind is something like this. So, I want to decompose my manifold into certain kinds of manifolds with corners. So this is a manifold with corners. But the picture is supposed to be a picture inside the symplectic manifold. So there's not going to be a base or something. It's just in the symplectic manifold, I'll give more details. And these chambers, these manifolds with corners, are supposed to intersect along faces. Okay, so this, very schematic picture.
So they're just what, submanifolds with corners?
Yes, there are submanifolds with corners, but there are special submanifolds with corners.
Right. So
yeah.
You don't want to give a hint.
Huh?
You don't want to give a hint. What do you have in mind?
Yeah, I can give a hint. So of course, so the faces of these are supposed to be defined by smooth functions like this, where they generate mu generates an S1 action. Okay, but this mu is only supposed to be defined kind of in a neighborhood of this face. Okay, and if I have two of these kind of local Hamiltonians which generate S1 actions, in the intersections, they're supposed to commute. Okay, so in a codimension 1 face, I have an S1 action. In a codimension 2 face, I have an S1 cross S1 action, and so on. And these manifolds with corners will have, faces of codimension at most n in a 2n dimensional manifold. So faces of codimension at most n.
Do you have, I'm a bit slow, either a theorem that such decomposition exists sufficiently often?
Yeah, so so there are two places where these are supposed to come from. So the first one is if you have, your Calabi-Yau. So let's here I have a degeneration, a maximal degeneration. Let's see. Degeneration of a calabia. So, you know, I have some, I don't know, actual smooth fiber here. And here I have, you know, something like this. Okay, so here I have this. So now, you know, I have a parallel transport maps. You know, you have, of course, it's very difficult to make this really precise, but there are if you take a path from the base, you can.
You mean it's kind of projection to the special fiber, retraction to
yes, yes, that's exactly what I mean. It's you follow you look at the Hamiltonian parallel transport maps, and you take the pre-images of, you know, let's say this follow, and this one comes here, and this one gives you one of the pieces. This one gives you the other piece. This one gives you the other piece. So you parallel transport the decomposition of the central fiber to the general fiber.
Mm-hmm.
Can I ask a question? Can you also think about it like from the SYZ point of view? That
yeah. So that's the second place in which these things might come from. So if you have a Lagrangian, if you have, let's say, M to B, some kind of Lagrangian torus fibration, then you could decompose the base into rational convex polytopes. Okay, and of course, because of singularities, you have to be, you know, you have to be careful what you mean by convex and so on. So there are different options. So for example, let me say something in dimension 2, where I don't know, maybe I have a K3 surface and it decomposes into this kind of S2 with 24 singularities in the base. Then you just, so the most basic thing that the thing that I'm happier about is a decomposition like this, where you just kind of encircle each of these, each of the singularities in the interior of these polygons. So I'm gonna kind of base my definition with this in mind. So in higher dimensions, this would say, so in each of these kind of chambers, the most singular fibers of an SYZ fibration will be in the interiors of these chambers. So here, 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 and so on. And you know, the ones that come from the previous dimension cross some S1 factor are allowed to cross the codimension 1 faces, and so on. So this is the thing that fits the best in what I want to describe, but it can also be extended to this toric degeneration picture, where you, in that case, you actually put singularities along the edges like this. But that's also okay. But I have to kind of, the definition would be more complicated to write. Does that answer the question?
Yeah. Thank you. So this polyhedral decomposition kind of transversal to the discriminant of the.
Yeah. So in my mind, I would like it to be indeed transversal to the discriminant, but it's somehow like there is much more literature on this kind of you know, let me just choose a pointer. This kind of singularities along the you know, the faces of the decomposition. There's a lot more literature on that. So like if you take this the usual picture for the quartic in P3, you know, it has this tetrahedron picture where all of the singularities are kind of along these edges. Okay, so in that case, I can consider this as one of the pieces in my decomposition, one of the chambers in the decomposition, like this. And you know, this is also what this fits with this kind of degeneration picture as well. But yeah, so I'm not gonna make the definition including this, but I'm pretty sure it can be included. It's just when you do it like this, when you consider this version, then these are not actually smooth. Like these hypersurfaces, the pre-images of these are not smooth. So this S1 action there is not free. There's some that level set is not a regular level set. So it just becomes a little. So what you have to say is like, okay, I have an S1 action that's free in some neighborhood of this, but not actually along the edge, which is also okay in the definition. Okay, maybe I'm actually saying more than what's asked.
No, this is fine. I mean, it's kind of symplectic analog of the story with Berkovich skeleton, where you also have actions of tori of different dimensions depending on the deepness of the singular stratum. Okay, good.
I think so, yes.
But that was precisely my question. So whether it's a yellow picture or it's, because the yellow picture is this Berkovich picture, but the symplectic picture should kind of be dual.
So I don't want to like, I actually don't have most of those structures. So I really just have a symplectic manifold and a decomposition of it into pieces. So I know it gets really confusing, dual Berkovich picture, dual intersection complex and so on. So
let's let him speak, because otherwise we will not hear.
No, I think these are great questions, but I just don't want you to like imagine that I'm secretly talking about some other picture. I really want to talk about this picture. Like, and you know, in the Lagrangian fibration case, I really have a fibration, like Lagrangian torus fibration. There's no holomorphic structure, nothing, just a symplectic manifold, a Lagrangian torus fibration, some grading data, and some decomposition of the base. So it's more like moment polytope picture. So what Gross-Siebert do, for example, they take this, they take its dual, and then from that, that's the dual intersection complex, and from that they run this scattering diagram algorithm. Okay, but for me, there's only one thing that exists. It's just there is a symplectic manifold. If you want a base, if you want a base with a decomposition, or just a decomposition in the total space, some version of that. So it's a weakening of that structure. Okay. 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 So essentially, what's going to happen is with this kind of decomposition, I'm going to construct a mirror formal scheme over Novikov ring. I'll write that, and then in order for me to set up the homological mirror symmetry functor, I'm going to need a Lagrangian, which is playing the role of a Lagrangian section. Okay, so it's not going to be a section because I don't actually have a fibration, but it's going to be a generalization of that. So if I did have a fibration, it would be a section. Okay. So then let me just say that. So given this data, I want to construct a mirror formal scheme over the Novikov ring. So the Novikov ring is, arbitrary coefficients. You can take integers or rational numbers, complex numbers, depending on what's going to come next. These might simplify the algebra, but from the perspective of geometry or Floer theory, any base ring is okay, commutative base ring, and it's a formal power series with non-negative real exponents. Okay, and the way I'm going to construct this formal scheme is I'm going to take this decomposition, and each of these chambers in the decomposition, I will be able to associate to it an algebra over the Novikov ring. Okay, so that algebra, why did it get stuck? Okay, so these relative symplectic cohomology algebras, and I will just try to glue their formal spectra. So the spoof of these things. And the gluing, the transition maps will come from each of these. So if you take two of them, like this one and this one, they both have restriction maps to this edge. And the edge has its own relative symplectic cohomology. And I will glue these two affine formal spectra along this affine open, this common affine open. Okay, so but I will have to justify that. For example, the restriction map from this big thing to its face is it corresponds to the inclusion of an affine formal scheme. So that's not going to be obvious. Okay, and then I want to construct from some kind of Fukaya category of Lagrangians so this I have this Y, and I will take a particular DG enhancement of the coherent sheaf category using this kind of defining affine cover. It's going to be some check model. And the functor will be set up by, I have this fixed Lagrangian. And for any Lagrangian that I'm given here, I'm going to kind of look at its Floer theory with this given Lagrangian. So I call this Lagrangian the reference Lagrangian. Okay. And then finally, the eventual goal is to identify when this functor is cohomologically full and faithful. But you don't really expect this cohomologically full and faithful over the Novikov ring, but you expect it over the field. So you want to replace this formal scheme with its Raynaud fiber or rigid analytification, the Berkovich space that you obtain by just canceling everything with the Novikov field. Yeah, but so to make that statement, you might want to assume that this base ring is C or some nice field. Okay, so I wrote this reg here. It's not something fancy. I will have some Novikov ring modules. And if I'm given a Novikov ring module, I can tensor it with the Novikov field, almost like the quotient field. And inside this, I have evaluation. I have a lattice inside this given by just A. And that gives me an evaluation. I look at the evaluation bigger than or equal to 0 elements. So this is just some stupid thing. Like you have this maximal ideal of the Novikov ring. If you do this operation to it, it will become the Novikov ring. Okay, so it's a regularization operation. It's very annoying that I have to do this, but it's actually crucial for the construction to work as I intended to. Okay, so the complex numbers don't appear in the story directly. It only appears after you kind of want to process what you constructed, if you want, in the algebra. And if most people are unhappy with this kind of non-Noetherian ring. And if you want something that's more discretized, something more like formal power series rings, what you should do is to pick some kind of Seidel type large volume limit data, by which I mean you choose a divisor inside M, a symplectic divisor, and you choose some primitive of the symplectic form in the complement of this divisor, such that the residues around the components of this is a normal crossings divisor. The residues are given positive numbers. Okay, if you're given this extra data, this large volume limit data, then sometimes you can construct models over models of this Y over formal power series rings, and then you just do a base change to get this mirror over the Novikov ring.
So I'm confused. This additional data, how they are related to this decomposition story?
Yeah. So this divisor is supposed to be dual. So it's supposed to appear. Okay. So let me. So that is my picture. So for example, if you have a base. So okay, let me just let's do. So this divisor is supposed to look like this. So this is where it kind of lives. But of course, there are circles. Looks kind of like this. So if in the SYZ picture, if you have an SYZ base, it looks like this. Something. Okay, so it's in the dual of the decomposition, and it's a symplectic object. Okay, so you have kind of how do I say this? So along each of these blue bits, each of these blue bits, they define an S1, the homology cycle in the total space. And if you extend that cycle in this direction, okay, so if you take a lift along those directions, so that becomes a Lagrangian, and you take that same S1, but you instead extend it above this red transverse curve, a transverse line, and that becomes a symplectic thing. Yes?
Mm-hmm.
Okay, and so I'm going to give a toy example, and I had given a talk about this toy example last year, but in a more general setup, in the setup of abelian varieties. Now I'm just going to talk about the torus. So, you know, it's on YouTube. You can find it if you want. So here's my example. So, I mean, I understand that the example that I'm covering is extremely simple and everyone understands everything about this example. But as I said, it's kind of conjectural. I hope that it will be much more general. But let me just talk about this example to just, you know, say where the pieces fit together. Okay, so first, my symplectic manifold is this torus. And the decomposition that I'm considering is the decomposition into these three finite cylinders. Okay, and each of these finite cylinders will have area AI, let's say. Okay, and then if I consider for each of these cylinders this relative symplectic cohomology algebra, it will be topologically generated by two variables, one living around here and another one living around here. So the generator, I put it outside, right outside, and this generator I put right outside. And so it's generated by those, meaning that, you know, I have this restricted formal powers series ring generated by these two variables. So I allow infinite series, but the exponents have to go to the exponents of the coefficients have to go to infinity. Okay, and then I mod out by this relation. So the product of this generator times this generator should be T to the area of the cylinder. Okay, so this is some kind of smoothing of this two transversely intersecting planes. If you set T equals 0, you will get two transversely intersecting planes, well, lines. And this is a smoothing of that. Because, you know, like a formal scheme over the Novikov ring whose special fiber is that. Okay, and now I'm saying that I have these restriction maps. So now I have to look at the relative symplectic cohomologies of these circles that are at intersections. So those are also generated by two variables. So now there's a generator right on the left, on the left and on the right of the cylinder. One of them is associated to this one, and this one is associated to this one. So the numbering follows that. And now the product of these two generators is now 1. There's no area here.
So I'm confused, sorry.
Yes.
Your CI is a symplectic object, yeah?
My CI is a subset of this symplectic. So
yes,
this
so it's symplectic, but CI, I plus 1, it's not symplectic.
It's not symplectic. It's not supposed to be symplectic. So this relative symplectic cohomology is defined for any complex subset.
So when you write, okay, so then you consider it as what? Because it's you write symplectic cohomology of
yes,
CI.
so I will go over.
Okay, all right. Okay.
I will go over what this is. Just want to tell you what this is supposed to output in a simple example. Okay. And then I have this guy, and this one is just like so I have this kind of punctured plane, and I kind of take its trivial smoothing, so already smooth. So now I have these two kinds of, so the algebras associated to the cylinders and the algebras associated to the intersections, and the map, the restriction maps that go from cylinders to intersections. So if there's a common generator to the two, then I just preserve that generator. It goes to itself. And for example, if I look at the map from C1 to the C12, and there's also this generator, and this generator goes to this generator. So this generator goes to this generator, to the one that's not common to the both, and it sends this one to T to the area times this one. Okay, so that you can see defines a map of algebras. And now I glue, so you know, I have the intersection, I have the inclusion of this into both sides, and I just keep gluing them. So here, for example, if you look at this side, it's here. And if you look at this C star here, or you know, the punctured plane, it's this one. Okay, so what I get in the end is a smoothing of this, this kind of what you expect to be the central fiber of the mirror. Okay, and
so okay, no, I'm looking at this picture with Lagrangian L. So do I understand correctly that instead of this Floer family homology, you choose just finitely many? You do not assume that each.
Yeah, so I'm not working at all with fibers. The fibers do not play a role in the. This is not family Floer homology.
Yeah, that's what I mean, because after all, your individual pieces CI they do fibered by circles, by Lagrangians, and so then you know you do not consider this home from L to the family.
No. Yeah. So just like every symplectic, every compact subset has symplectic cohomology. Every compact subset also has, for any ambient Lagrangian, it also has some relative Lagrangian Floer homology. All about wrapping near the boundary. It's just if you're given this Lagrangian and this compact subset, what it's going to do essentially is going to wrap around the boundary of this compact subset many times. That's what the definition is going to be. But it's again not Floer theory of L with CI. It's Floer theory of L, so let's say supported at CI.
Okay.
Yeah. So with that definition, so this with this section Lagrangian, actually this zero relative symplectic cohomology is going to be just relative Lagrangian Floer homology of this Lagrangian. Essentially it's just the one chords of this kind of boundary wrapping is the same as the one periodic orbits of this. That's essentially what this is going to boil down to. Okay, so then you could actually do this entire construction using this Lagrangian section. And then if you do that, then you can also set up this Lagrangian, mirror symmetry, homological mirror symmetry functor by using the fact that this Lagrangian Floer homology acts on this pair. So now I have actually two Lagrangians, one this, and this blue is any other Lagrangian. And now I can also do the Lagrangian Floer homology of a pair of Lagrangians, again, supported at this compact subset. And then this acts on this in the usual way. And that's how you set up so then, if you want to set up the homological mirror symmetry functor for this L prime, then you just send it to this diagram of modules. Okay, so that's kind of the basic story. So I am already half an hour into my talk, so obviously I'm not going to finish. But okay, so let me give you a very quick review of this relative symplectic cohomology. So I have M and I have any compact subset. And so an acceleration data for this compact subset is just a family of functions which converge to 0 inside K and they converge to infinity outside K. Okay, any monotone sequence of functions. And I also have to pick some interpolating data as well, and many other kinds of like almost complex structures and so on. But basic data is that I choose a family of a sequence of functions that converge to 0 inside K and plus infinity outside K. And I can also fix two Lagrangians. These Lagrangians can be the same or different, but for simplicity now I'm going to assume that they are tautologically unobstructed. Okay, so let me just do that. So now doing Hamiltonian Floer theory, I obtain these two diagrams of chain complexes. Okay, so So for each Hamiltonian, I can talk about its Hamiltonian Floer homology. So that's something that's generated by the one periodic orbits of this Hamiltonian. And there's some differential obtained by counting some solutions of the Floer equation. And similarly, I can, if I have a pair of Lagrangians, instead of looking at one periodic orbits, I look at one chord. So I have this Lagrangian here, the other Lagrangian here, and I just look at all the, all the one chords, which means, you start at this L, follow the flow of H, and then you end up at this other Lagrangian for time one. Okay, so these are, it's a fixed time. It's the time for which, so you could take Hamiltonians to be time independent here. In that case, you want to fix a time. And if you want them to be time dependent, then you want them to be defined on the interval 0, 1, and then you're going to look at time one chords. Okay, and again, the differential is defined by counting Floer solutions. And I also have these natural maps between these two chain complexes. These are chain maps. And again, I count Floer solution. Okay. So I'm also going to use this completion functor for modules over this Novikov ring. It's defined in the usual way as the inverse limit of truncations. Okay, so I have this kind of diagram of chain complexes. It's it's a one ray. They form a ray, and you're supposed to take some kind of homotopy colimit. Any model of homotopy colimit is fine of this diagram, and then you obtain the telescope or the homotopy colimit chain complex, and then you're supposed to take a degree-wise completion. Okay, so that's the definition of, and then you can take its homology. So the homology of this thing is going to be the relative symplectic cohomology of this subset. Okay, and then the story is the same for in the Lagrangian case. Again, you look at this telescope or homotopy colimit of this diagram, and then you do a degree-wise completion. Okay, and then the point is that even though we made some choices here, this choice of acceleration data, the homologies are independent of those choices. They only depend on the compact subset and then the Lagrangians here. So again, I mean, this is just some rigorous way of doing wrapping near the boundary. Okay, but the thing maybe that I want to stress is that these Hamiltonians and everything is defined in the entire manifold. Okay, K enters into the discussion by prescribing what functions I'm using to do Hamiltonian Floer theory. Okay, and if I have nested compact subsets, then I have restriction maps as well. Okay, so now this has a lot of extra structures. So for example, relative symplectic cohomology, this is a closed string invariant. It can be equipped with a BB algebra structure. So again, you count certain kinds of curves, and if you want the product, you do a pair of pens kind of count and so on. So this one's not unital because the unit actually wants to live in this kind of valuation 0. So you tensor it with lambda, and then you have a unit, and the unit lives in valuation 0 at the 0 part of this. So this has to do with this kind of technical thing that I have to take the regularization, what I called regularization anyways. And moreover, so I talked about only cohomology level structures. There's actually a chain level model of this thing, a much bigger model than what I gave you in the previous slide, which admits an action of the framed E2 operand, the chains on the framed E2 operand. Okay, so these are all expected structures of closed string. But so normally, you have, this is part of the structure of quantum cohomology, for example. And quantum cohomology is just a special case of this construction where you take M to be a closed manifold and K to be the entire manifold. Then you get quantum cohomology, and you recover.
BV algebra structure follows from this E2 framed structure.
Yes, of course, yes. I just wrote them in kind of increasing amount of, yes, of course, this is the chain level statement. So this is the homology level statement. This is the chain level version of that homology level statement. So it's a stronger thing. Yes, I agree.
Mm-hmm.
And more in the Lagrangian case, again, I'm assuming tautologically unobstructed, so no disks. You can allow disks, but the statements are more complicated. And so in that case, if you choose the Lagrangians to be the same, it should just be an associative algebra. And this is supposed to be a module over that associative algebra. The pair is supposed to be a module over that associative algebra. And if you assume tautologically unobstructed, again, you can have chain level statements, like this is actually an A infinity algebra, this is an A infinity module over that A infinity algebra, and so on. And in fact, you can also just set up the Fukaya category, but under the assumption that the objects are tautologically unobstructed Lagrangians. Okay, so that's not that difficult. What's difficult is when there's curvature in the A infinity algebra, then that construction is more involved, and it's not in the literature yet. Moreover, you have more structures. You have open closed and closed open maps. So you can make these kinds of counts where, for example, let's look at this one. So this one has some Lagrangian here. So I have some Lagrangian Floer homology kind of input here. Here I have a closed string output, like a Hamiltonian Floer homology of a one periodic Hamiltonian kind of output. So that's going to define at the end of the day for me a map that goes from the Lagrangian Floer homology of this Lagrangian that I put here to the relative symplectic cohomology, but I'm also allowed to have this K here. Okay? So without the K, these are again standard structures, but now I can also put the K's here. Okay. And so there's also closed open maps, which goes in the other direction. So this one is so this one's easier to say. This one's an algebra map. This is an algebra, this is an algebra, and this respects the algebra structures. The open closed map is not an algebra map. It's a module map where you act. So you act, it's a module map over the action of relative symplectic cohomology. It just acts on it in the usual way. And here you first have to go to this, and then this acts on itself. Okay, and in fact, you can just set up the entire Cardi diagram, and this actually is replaced with the Hochschild cohomology. This one is replaced with Hochschild homology, and so on. So, there is this whole kind of generation criterion business, where if this map here hits the unit, this Lagrangian L, it can be used to generate every object of the Fukaya category. This is kind of the Abouzeid generation criterion. So there are some versions of that here as well, which I'm not going to spell out, but so this is part of what I'm assuming for the construction, for the conjectures that I'm going to tell you to work. Okay, and moreover, you need to construct more things to get the full power of homological mirror symmetry. You should actually set up this Fukaya categories for all Lagrangian braids, not just for tautologically unobstructed ones. And this is ongoing work. And it's been ongoing for a while, but I mean, we're making progress. It's just technical. Okay, so now let me quickly say what this chambers that I was telling you are, in some kind of way of making this rigorous, this notion rigorous. So I'm calling these chambers generalized Delzant domains. So these are just subsets of my symplectic manifold, and they're just going to be like codimension 0 submanifolds with corners. So there are these functions that are defined in a neighborhood of this subdomain, such that they, if you look at the places where these functions are non-positive and take their intersection, you get your generalized subdomain, the C. And the C is a manifold with corners whose faces are exactly given by the vanishing of these functions. And so the face poset of this manifold with corners is actually, it should be simplicial. This is not actually that big of a, it just says that if you have a codimension K face, that should be given by the intersection of K codimension 1 faces. because that's what it means for it to be simplicial. So like, for example, you can't have something that looks like this, because the intersection of these two faces is this union. That's not allowed. This is allowed. Okay, I mean, the rest of it is not there. The extensions of these edges are not there. It's just easier to draw that way. And it should be of dimension n, which means that it should have a codimension n face. Okay, mu j's generate Hamiltonian circle actions near their faces. So as I was saying, if you have something that's defined by these functions near the this is the mu j equals 0, then in a neighborhood of it, this generates an S1 action. And as I said, I will assume some freeness of the action, but this can be relaxed. Oh, and I also forgot to say they commute at the intersections. Oh, sorry, I went too fast. So they commute at the intersections, and therefore at the, let's say I have two intersection of two codimension 1 faces, which is a codimension 2 face. Here I have a T2 action. So I'm assuming all of these actions are simple, free for simplicity. But as I said, I think this can be relaxed. It's just it takes too long to write what the relaxation is. And I also need to assume that this grading data that I chose in the beginning, it should be in some sense invariant under these circle actions. Okay, so another statement that would take a while if you were to write it precisely. Okay, and then you can see that each face of this generalized Delzant domain is a coisotropic, and the characteristic, if you look at the leaves of the characteristic foliation of these coisotropic submanifolds, they are given by tori of dimension equal to the codimension of their face. So for example, if you're in a codimension 1 face, then you just have a circle action. So you have just circle vibration. But if you look at a codimension n face, that's just given by a Lagrangian torus. And there's nothing else, just a Lagrangian torus. And everything in between. So, even with this, I lied because I actually need a colored version of this. So I don't want just one level to satisfy this. I want, like some neighborhood of levels for each of the faces. Okay, so it's some kind of coloring of that. Okay, so then I want to cover by these subsets. And cover is just, I take a locally finite cover such that the intersection of any two is a connected face or empty. Empty, I think of maybe as a connected face too, but they could be empty or they could intersect along faces, connected faces. And so if you look at any, let's say I see something like this, I have this is a codimension K face. Okay, maybe this one is a codimension K face. It's common to many chambers, many generalized Delzant domains. But so what I want is that, essentially what I want is that, so that I have a bunch of functions that are defined in neighborhoods of the faces that kind of join at this point. I want all of those to Poisson commute. Okay, but like a weaker statement that there is some map to, let's say this is codimension 2. So there should be a map to R2. And in the base of this map, there should be some decomposition. Okay, and it just only in this neighborhood, the subset should be obtained by looking at pre-images. Okay. Okay, so then in this situation, what I proved in my thesis some 4 or 5 years ago is that there is some local to global principle. So there is a spectral sequence, let's say M is closed, and I take a finite cover by these things. Then there's a spectral sequence converging to quantum cohomology. And in the first page of the spectral sequence, you have this kind of relative symplectic cohomologies of intersections of this decomposition. So so maybe I come here. So this this spectral sequence is obtained by, let's kind of slightly, I have to be careful when I'm saying this, but let me just be a little bit vague here. So it comes from a double complex. Okay, so I have the the relative symplectic cohomologies, chain level versions of just the chambers, double intersections of the chambers, triple intersections of the chambers, and so on. Okay, so here I have this restriction maps, chain level restriction maps. And here I have Floer differentials. Okay, so this is a double complex if you set it up correctly. And the homology of this total complex, if you look at the total complex and take its homology, that's isomorphic to quantum cohomology. That's what I proved in my thesis. Okay, and in order to get the spectral sequence, you first take the Floer differentials. So up, going up. So you just get relative symplectic cohomologies here. And the induced differential on the first page is just the check differential, but it could continue. Okay, so there's this spectral sequence. And for example, if you have a cover by two elements, two subsets, then this is equivalent to a Meyer-Vietoris property. Okay, so this is what's going to tell me that, when I make my construction, like I told you, from local pieces, the global invariants will kind of have a chance of matching for very natural reasons. Okay, so as I explained in the beginning, this was inspired by kind of degenerations of complex Calabi-Yaos, and we would parallel transport the decomposition to the central fiber. That's how we obtain it. In the SYZ viewpoint, we decompose the base and lift polytopes from the base. I said all of this, so I'm skipping quickly. This is about the discriminant locus question. So in the natural, in the situation that seems most natural to me, but somehow it's harder to construct, it seems, in examples, at least in the literature, is that the discriminant locus should be dual to this. So the most singular fibers are contained in the interiors of the chambers and so on. But again, like I kind of very sketchily said, this toric degeneration picture where you actually put the singularities along the faces, it can also be made to, I think, fit in this picture by slightly relaxing the definitions. Okay, so now I want to tell you the key conjectures for the construction to work. Okay, so now I have this relative symplectic cohomologies of each of these pieces, and I want to compose that with this regularization functor. Okay, so I just kind of do this trivial looking operation, and I get a presheaf of commutative algebras on all compact subsets of my manifold. Okay, so then let's take a generalized Delzant domain with face poset. So, I have this kind of poset of faces of this generalized Delzant domain that I'm going to all consider as subsets of M. And I will look at their relative symplectic cohomology. So, okay, my first kind of part of the key conjecture is that these cohomology algebras are actually theoretically complete and separated. So I did a completion at the chain level. So it's complete at the chain level, but when I take homology, it doesn't necessarily, it doesn't have to be separated. You can lose Hausdorffness, and I claim that you don't in this particular case with generalized Delzant domains because of some convexity. Okay. This thing should be theoretically complete and separated. And this low energy as part of the conjecture is probably the most serious part. I claim that there exists some hbar that depends on this generalized Delzant domain with the property that if I consider my sheaf relative symplectic homology and list it, I just look at its values on the faces, including the entire chamber of the faces of this generalized Delzant domain. I want to be able to say that if I truncate everything at level hbar, that's actually a combinatorial thing. Even though I'm doing all this Floer theory and so on, all the contributions to it are actually kind of constant solutions with energy 0 in the limit, and it's combinatorial. Okay, so I claim that it's isomorphic to this other pre-sheaf on this phase poset. It's this SR is for Stanley Reisner, and it's kind of what you expect if you've seen this before. So it's generated. So at every phase, it's generated by the codimension 1 phases that that intersect the given phase F. Okay? The ones generated by the ones that intersect. And then you mod out by the relation that if you have some of these codimension 1 phases, which all intersect the given F, the given phase, but these codimension 1 phases themselves don't intersect, they don't have any common point, then you actually mod out by the product of those. Those should, their product should be 0. And if this codimension 1 phase that intersect J actually contains J, then I also adjoin its inverse. Okay, so that's this Stanley Reisner. It's not just one ring, but it's a pre-sheaf over this phase poset, and I extend that. So this should be K. I extend this sheaf that's just defined over my base field to this truncated Novikov ring. Okay, so that should be the answer. I should be able to kind of find a small constant such that when I truncate everything with that constant, what I get is the expected combinatorial object. Okay. And the last thing, the last part of my key conjecture, it has 3 parts, is that the restriction maps, when you look at this, when you restrict the sheaf to the phase poset, they should be injected. So this injectivity, I mean, there are some geometric reasons to expect it, but in the mirror, if you want to think about mirror symmetry, it's supposed to be related to unique analytic continuation. Okay, so, I think I don't have to maybe. So these are like functions. If you restrict functions and they agree on a germ of a point, then they're actually the same function. So that's what this is about. No. Okay, sorry about this.
Your non-Archimedean geometry is just conventional Tate, which means that, or is it Berkovich?
You can do, I have something stronger than non-Archimedean. So instead of taking these rings over the Novikov ring and taking their formal spectrum, I could tensor them with the Novikov field and take Berkovich spectrum and then glue.
Yes.
That's something that you can recover from the formal scheme.
No, but you impose some properties for the answer to give you in the end some sheaf of whatever algebras, anyway, some non-Archimedean space, and these properties kind of, if you, since Berkovich spectrum, I mean, in Berkovich story spaces are sort of connect Hausdorff, I would say. So then there might be some properties which.
Yes. So for example, I think something that's a very interesting question is, can you find geometric meanings of the points of the Berkovich space? So the Berkovich space has many extra points, right? It's not just the maximal ideals.
Not at all. No, it's
not at all. So those points probably also have some kind of traces in the A side.
I mean, since they're semi-norms, they probably should be defined in terms of some behavior at some infinity or something like that. You have these functions and you look how they grow when you approach some strata at infinity or something. I mean, it's...
maybe not, maybe I don't know strata infinity, but subsets. Like,
maybe subsets, yeah, something
maybe
like
for example, Lagrangians, like any Lagrangian.
Yeah.
You could look at this closed open maps, and there's going to be some areas involved there.
Yeah.
So and you can take you can think of those areas as maybe defining something like a seminar. I mean, pure speculation, but I think that there is possibility.
Yeah, I understand. Yeah.
Something like this. Okay, so maybe let me also say, I think everyone already guesses what the construction is, but I just want to point out that unless I'm missing something, if you assume these three properties, which I claim can be proven, they're very provable properties from, I think, from a Floer theory viewpoint, then you can formally prove this following thing, that this regularized relative symplectic cohomology in degree 0 algebras are actually admissible algebras, which means they are topologically finitely presented, and they're, by definition, they don't have any torsion. But the key point is this topologically finitely presented. I mean, even just finitely generated. So if you take an arbitrary compact subset in your symplectic manifold, it has a relative symplectic cohomology, but it won't be finitely generated. But these ones, because of this kind of piecewise linear structure, they are finitely generated. Okay, I'm just going to say as much. And then if you look at this kind of, you have this restriction map from the big set to the double intersections, and you look at the kind of induced map on formal schemes, then this actually has open image, and it's just an affine open inside here. The image is an affine open here, and the reason why this is true is something like this. So you have a chamber, and you look at restriction to some face. So this is essentially given by, so I have a generator, let's say I have some kind of generator associated to this. I have this generator modulo t to the h bar, and I can take an arbitrary lift. It's not canonically defined, but I just take an arbitrary lift, and that generator becomes invertible when you pass to this subset by the restriction map. So this restriction map is actually a localization map, some kind of completed localization map, inverting this element, this lift of the canonically defined element modulo t to the h bar. Okay, so that's how you define, that's how you show that these, gluing is possible. Well, this is the second part. You also need a cocycle property. And the cocycle property is also true because if you have something like this, triple intersection, this, so here, so here, what you have is so you have the relative symplectic cohomology of this triple thing, and that's going to be isomorphic to kind of you localize at this generator, you localize at this generator, and you look at the intersection of those two. And you can prove that this statement about localization here, it also just localizes at those two generators. Okay, so, I didn't manage to say this very well, but the cocycle condition also is satisfied for some good reason. Okay, and then we glue these, these formal affine schemes along these open intersections. And as I said, you can, if you want something that immediately lands in the non-Archimedean world, a non-Archimedean geometry world like Berkovich spaces and so on, you, instead of taking spoof here, you just take tensor, you tensor this with the Novikov field, then this topologically finitely presented condition tells you that it's actually affinoid algebra. So you can take this Berkovich spectrum, and then you can glue those. Like this localization maps correspond to affinoid subdomains and so on. So you could immediately just construct Berkovich space. Okay, so now, I'm almost done. So let me at least finish the slide, maybe. So this construction, I think, is very natural, but we don't want just the construction. So there are many other constructions too, but we want to really be able to prove either homological mirror symmetry or maybe closed string consequences and so on. So we can't stop here. So something that I think that it's what I said is because of this kind of low energy limit. We know that the low energy limit is simple. You know what the central fiber of this thing is, and it's what you expect. If you constructed the mirror using, I don't know, any other method where you had a smoothing, not just the generic fiber, then it would be the same. But what I don't know anything about is what this mirror scheme is. Okay, so that's something that this approach says nothing about. I'm not telling you how to compute it at all. I'm just saying it exists. So here, my goal, I mean, different people might have different goals using similar constructions. My goal is to construct something and prove the consequence of the mirror, and not necessarily identify it. That's, to me, a secondary step. I mean, I'm not saying this is the best thing. I feel like the construction is good for that, not good for computing the mirror, but showing that there exists a mirror satisfying homological mirror symmetry and so on. And then, if you really need to, then maybe you have to compute this. And that I'm not saying anything about. In this
but to this point, I mean, if you consider this SYZ picture, then you can compute mirror in terms of some data on the base of this Lagrangian torus vibration, yeah?
I mean, you expect that you could, like you have some standard, let's say list of singularities, and they all have some neighborhoods, and you could probably compute it, but I'm not saying anything about that. It's just a separate step.
Yeah, I mean that since you also have some decomposition into some simpler pieces, so you can kind of, I don't know, there is no analog of the base. Yeah.
The goal, the hope is not the hope. I mean, if this works, then it should be that. But like, for example, even in the K3 case, let's say you have a K3, there's some S2, and you take some neighborhood of this. So, you would think that you know the answer to what the relative symplectic cohomology of this is. Mm-hmm. If this was just contained, so this is something you can also think of it as a subset inside just, some local manifold. So some complete local manifold, no other singularities. So here, this one you can compute. This is what we did with this paper with UL. And there are other ways to compute too. But can you really say that this computation agrees with this computation where the rest of the manifold has changed? I think in this K3 case, yes, and UL, I think, is working on this. But for example, I'm not working on this. Like, I would like to not work on this.
So
at least not at this stage.
Device. Yeah, it's rather theoretical device. Then you have mirror, but if you would like to prove homological mirror symmetry for that mirror, it's not clear. I mean, it should not be some standard procedure which uses, I don't know, ideas of Floer family or.
But none of these things actually work to like the family Floer mirror is not actually defined on the singular fibers.
Yeah, I understand, but sort of mimicking, generalizing, or doing something, it should be completely different way to prove because you have no control on the geometry. For example, I don't know, if you start with like this K3 or whatever other Lagrangian torus vibration, can you show that this, I don't know, essential spectrum of this mirror dual thing is isomorphic to the base of the Lagrangian torus vibration, that your story agrees. I mean, this what SYZ predicts.
This I expect. You can also, so I think you don't have to, in order to construct the non-Archimedean SYZ fibration of the mirror, you don't need to actually have a computation. So you have this degeneration, and you also get a canonically defined holomorphic volume form. So I think by using your work with conservation plus all this other work on non-Archimedean SYZ fibrations, I think you get immediately a retraction onto the Berkovich skeleton.
Yeah. But if follow your procedure and
and I think you can prove that base is the same base. Yes.
Okay. Mm-hmm.
Yes. Yeah, but that doesn't mean the total space of this non-Archimedean SYZ fibration, right? I mean, I think there are some expectations that there's a unique thing upstairs, but I think so far it's still expectations, right?
Yes. But if you have an analog of the base, then at least you can conjecture what the answer is.
Yes. This I agree. Yes. Yeah, I mean, I believe that this locality thing holds, by the way. I'm not saying it doesn't hold. It just holds. Like I said, this model, this thing contained in K3, and this local model, they're isomorphic, but not canonically. You have to make some choices to get this isomorphism, and this kind of different isomorphisms correspond to wall crossing.
Yeah, that's exactly what I wanted to ask. Yeah, yes. The wall crossing should take care about this.
Yes, but like most of the other approaches start by assuming wall crossing works and kind of uses that as input, right? Here, I want to do the opposite. Like, yes, there is wall crossing, but I'm never actually identifying this with its local model. I don't have to do that.
Mm-hmm.
Okay, yeah, so I'm done. So let me just end by saying what I didn't have time to say. Maybe it was just unrealistic to begin with. So if you want, so there are some, so after this construction, there are some statements that you can make. For example, you can prove that functions in the mirror over the you go to the non-Archimedean world, the functions on that is isomorphic to just the relative symplectic cohomology of M. Of course, this is a trivial statement. If M is compact and F is not compact, then you have to define this as an inverse limit. But then this statement is actually not that trivial. It's still something. So, but when M is compact, then both of these are just kind of one dimension. So there's not much to it. But for anything more than just this, you need, at least in my viewpoint, I don't see how to do it without choosing this Lagrangian. So now I actually have to start working with the Lagrangian if I want to say anything more. Okay, so this is where I end my talk. And then I had this kind of definition of reference Lagrangian, even more sketchy, even more conjectural part. But I don't think that with just this you can prove homological mirror symmetry. I think you need more. Okay, thank you for listening.
Okay, thank you very much. Very interesting talk, and kind of much clarified, much more from the previous talk on the same subject, I would say. All right, so more questions. So from the geometric point of view, this assumption on the existing of this Delzant, whatever, decomposition, it's kind of your main geometric proposal, like, because people impose some restrictions on singularities previously and blah, blah, blah. And so this existence of Ci with nice properties, that's your main geometric kind of, is it correct?
I think so. Geometrically, yeah, I'm just suggesting a framework in which you can maybe more easily construct the structure than.
Okay.
But I'm also not aware of so I think setting up this homological mirror symmetry functor is also not like, for example, Gross-Siebert program. I think it's very difficult to set up the homological mirror symmetry functor. You starting with that. Like, I think that's another thing that should be kind of like, even for example, like because of this local to global property that I said with the spectral sequence, like you have a so I said that there are some natural maps between kind of this regularized relative symplectic homology, but now I'm looking at all degrees. So there are some natural maps from this to polyderivations on the local pieces. Okay, so the 0th degree is SH0, just functions. First degree, I just have derivations, so I get like vector fields, and second degree, I get bivector fields and so on. But this thing, under this condition of existence of reference Lagrangian, these maps should actually be isomorphisms after tensoring with lambda. Okay, so then this spectral sequence thing that I showed you, it's kind of like the Hochschild-Deram spectral sequence on the other side. So you kind of get automatic agreement of global invariants, like quantum cohomology on one side, and just Deram cohomology on the other side. I think this, for example, if you do family Floer theory, I don't think you get this.
No, this is better. Yeah. Okay, thank you. More questions? Can I ask you to email me the slides with your kind of corrections and notes? So kind of it will be last. Yeah, I mean these slides with all that stuff which illustrates. Yeah, it will be, I think, more convenient.
Yeah, I can just send this to you as it is. Is that okay?
Yeah, that's fine. Absolutely. Okay, well, if there are no more questions, thank you very much.
I thank you. Thank you for listening. Thank you for inviting.
This is it for today.